Okay, it is my pleasure to introduce the speaker of today. So this is Jonathan Hickman from the University of Edinburgh. He's going to talk about Kakeya maximal estimates via real algebraic geometry.
Okay, so thanks, Kelowna, and to the organisers for the opportunity to speak in this seminar. It's a nice pleasure to be talking. So yes, I'm going to talk about some work on Kakeya maximal inequality. So this is actually a little bit old now. It's from a couple of years ago, but I've started to revisit these problems recently. So at least for me, it's nice to talk about them and refresh my memory of what's going on. So everything I'm presenting is joint work with Keith Rogers, who's in the Ethermat in Madrid, and Rushang Zhang, who's now in Berkeley. So I'm going to talk about the Kakeya maximal operator. And the study of this object can be thought of a problem in what I'll refer to as continuum incidence geometry. So I'm going to really emphasize the relationship between this problem and topics in incidence geometry in this talk. So to start off with, I want to discuss what classical incidence geometry entails. So a typical problem in classical incidence geometry is as follows. So I'm going to let this fancy L denote a set of lines in the plane, and I want to bound the number of k-rich points. So what I mean by this is I want to bound the number of points which line at least k of the lines from L. So these are the k-rich points. Now, we don't expect there to be a huge number of these k-rich points, and that's simply due to the following fact. So if we have a pair of distinct lines, we know they can meet in at most one point. And if they're distinct lines, we know they can meet in well, okay, for non-parallel lines, we know that they meet at exactly one point. So this should limit the number of k-rich points formed by our line set. And indeed, we have this very simple lemma, which just utilizes this basic fact. And it says the cardinality of the set of k-rich points is bounded above by the cardinality of the line set squared, and then multiplied by this factor of 1 over k squared. So of course, as k gets larger, it's more and more difficult for a point to be k-rich. So we see that this the number of k-rich points kind of shrinks by a factor of 1 over k squared from this bound. And as you can imagine, this is a pretty simple inequality. It just follows from Cauchy-Schwarz and the fact. So we get the square out of the Cauchy-Schwarz inequality. Now, what's interesting is that we can actually do better, and this turns out not to be the sharp bound. And this is the content of the famous Zemmeredi-Trotter theorem, which is a kind of fundamental theorem in this area of instance geometry. So this says if we have the setup I described earlier, so L is a set of lines in the plane, then the number of k-rich points can be bounded by this quantity you see on the slide. So this involves two terms. So one of the terms is 1 over k times cardinality of L. That only really comes up in kind of degenerate situations. So I'll really only focus on the first term. And in the first term, we see that we've improved the 1 over k squared L squared to 1 over k cubed L squared. So we've gained a factor of 1 over k. And this turns out to be the right bound. So I want to make some remarks. The first remark is that the fact alone is not sufficient to prove the Zemmeredi-Trotter theorem. So the fact is just a basic statement from, say, affine geometry. And it turns out that this Zemmeredi-Trotter theorem goes a bit deeper than just affine geometry. And more precisely, some kind of topological input is required. And one way you can see this is that, well, we can formulate all these problems over fields. And if we work over a finite field, which has a completely different topology, then the simple bound 1 over k squared times the cardinality of line set squared, this turns out to be sharp. Okay, so the Zemmeredi-Trotter theorem somehow distinguishes between the Euclidean space and these finite fields. It's not just a fact about affine geometry, it incorporates the topology of the continuum. Okie dokie. So in this talk, I'm going to move away from classical instance geometry, and we're going to be working on continuum variants of these kind of results. So what I mean by this specifically is that we're going to introduce some small scale, which is this little delta, And we're going to replace these lines with other geometric objects called delta tubes. So for a delta tube, we just take a unit line segment and we fatten it up by this little delta scale. So we look at the delta neighborhood of the unit line segment. And instead of counting cardinalities of k-rich points, we're going to be interested in, well, continuum counts of the k-rich points. So measures and LP spaces play a role. So one way to study information about these k-rich points is to look at this function I've written at the bottom right of the slide here. This is what I'll refer to as the multiplicity function for a collection of delta tubes T. So this is just the sum of characteristic functions of the tube. So if you evaluate this at any given point, it tells you how many tubes pass through that point. And we'd like to understand the distribution of this function. That tells us the distribution of the k-rich points. For instance, the superlevel sets of this function are exactly the sets of k-rich points. So in order to do that, we can look at things like the LP norm, which measure the distribution in some way. Okie dokie. So when we pass into this continuum setting, we can translate a lot of the facts from the discrete world over directly. But typically one has to incorporate kind of quantified information. So we have to quantify various concepts. So for instance, we could take our basic fact that two lines intersected at most one point. Well, in the continuum setting, we have to kind of quantify well, various things in this statement. So first of all, instead of looking at, say, distinct lines, we have to say that the lines are quantitatively distinct. So there'll be some, so here I'm saying two delta tubes that point in well-separated directions. So we quantify their separation in some way. And then we quantify the statement that they meet in they intersect at one point by saying, well, they meet on a set of small measure. And this could be made precise by this very elementary bound. So here we have the volume of the intersection of these two delta tubes, and we can bound it in terms of, well, this obviously it involves this parameter delta and also the angle between the tubes. So we have like some kind of quantitative bound that depends on the separation parameter between the two tubes. Okay. So the key question I'm interested in here is that we suppose T is a collection of delta tubes which point in delta separated directions. So all I mean by this is if we look at the directions of these tubes, consider them as points on the unit sphere, then these are delta separated on the unit sphere. Okay. Now, our question is, well, what can we say about the distribution of these k-rich points? And the idea is that if the tubes point in different directions, well, they can't overlap. Well, imagine if they're at right angles to one another, then they pass straight through one another. They can't overlap too much. So this should give us some kind of non-trivial control on the number of these k-rich points. So using just the fact, so by the fact I mean this quantified quantification of the intersection between two of these direction separated tubes. So we can prove the following classical theorems. This is due to Cordoba, and it's from the 1970s. It's a pretty old result. So if we have a collection of these delta separated, direction separated delta tubes in the plane, then if we look at the L2 norm of this multiplicity function, well, we can bound it by the sum of the volumes of the tubes raised to the 1/2 power times some logarithmic factor. So in this talk, I'm not going to be too worried about these kind of logarithmic terms, so I'll more or less ignore them. I'll remark that we can see that this kind of bound tells us some geometric information about the k-rich points. So for instance, we can bound the measures of the sets of k-rich points just by applying Chebyshev's inequality. Okay. I would like to try and give you some more intuition for what this kind of inequality means. So I'm going to try and to unpack the statement a little bit. So I've just carried on to the next slide, the statement of this Cordoba estimate. And here you see I'm suppressing these logarithmic terms with this kind of double wiggles notation. And I just want to do a small computation. So I'm going to take the expression which appears in brackets on the right-hand side. So that's the sum of the volumes of the tubes. And then I'm going to apply linearity to the integral, interchange, integration, and summation. And at this point, I'm just going to apply the Cauchy-Schwarz inequality. So I can bound this by the volume of the support of this multiplicity function, which is just the union of all the tubes, raised to the 1/2 power, times the L2 norm of the multiplicity function. Now, at this stage, it's obvious that we're just going to apply the Cordoba estimate. So we just plug this in to bound the L2 norm. And we have the following expression. And you see, after we've applied the Cordoba estimate, we have the same sum of the volumes of the tubes appearing on the left and right-hand side. So we can cancel out these factors. And what we're left with is this bound, which says that we can bound the volume of the union of the tubes below by the sum of the volumes of the tubes. Okay. So of course, we know that for, well, general unions of measurable sets, that the reverse inequality holds. And we know that the equality case holds when your sets are disjoint. So one, at least, interpretation of this, this consequence of the Cordoba estimate is that these direction-separated tubes in the plane are essentially disjoint. Up to a logarithmic factor, they're close to satisfying the equality in the or the additivity property of the measure. Okay. Do we have any questions about this? Okie dokie. So this is the case in 2 dimensions, but the high dimensional case of these problems is very poorly understood, although there is a conjecture, and this is what's referred to as the Kakeya maximal conjecture. So here I'm going to let T be a direction-separated family of delta tubes now in this higher dimensional Euclidean space Rn. And the conjecture is that there should be an analog of this Cordoba estimate. But now, instead of working with L2 norms, it turns out that the right exponent is this n over n minus 1 exponent. And of course, when you plug in n equals 2, we recover Cordoba. However, for n equals 3 and higher, only partial results are known. We're actually really far from fully understanding this problem. So I'd like to just have a small aside where I try to explain or give you some hint at why this problem is interesting. So these Kakeya maximal estimates are related to a whole host of problems in harmonic analysis. This is a famous chain of implications coming from a paper of Tau from about 20 years ago. And you see that the Kakeya maximal inequality is kind of low down in this chain. And all these other results kind of imply it in one way or another. And these are various problems related to convergence of Fourier series and certain problems in PDE. And it turns out that if the Kakeya maximal, or this Kakeya set conjecture failed, then one could use this geometry of these, use the resulting configurations of tubes to cook up counterexamples to all these different problems. So somehow at the moment, harmonic analysis, at least the central topics in harmonic analysis, are on somewhat shaky foundations, because we can't rule out these kind of counterexamples until we've resolved this Kakeya maximal problem. However, this is just one small chain of implications in this like kind of wider web of problems in harmonic analysis and related topics. So the Kakeya maximal conjecture somehow is a central problem in the area. Okay, so this is a little bit of an aside. I want to go back to describing some immediate consequences of this maximal conjecture. So first of all, you can apply the same elementary argument as I sketched earlier, but this time basically using Helder's inequality instead of Cauchy-Schwarz. And you can show that one consequence of the Kakeya maximal inequality is that, well, direction-separated tubes in Rn are essentially disjoint in the same manner as described earlier. The Kakeya maximal inequality also conjecture also implies the famous Kakeya set conjecture. So I don't really want to talk about this problem too much, but this says that the Hausdorff dimension of Kakeya sets in Rn is always n, where a Kakeya set is a subset of Rn that contains a unit line segment in every direction. So in some sense, the Kakeya maximal conjecture is like a function, can be understood as a functional version of this Kakeya set conjecture. Now, although the Kakeya maximal conjecture is a very difficult problem and we don't have much idea how to solve it in full, there are some estimates for these multiplicity functions which are very easy to obtain. So one very, very easy estimate is this L infinity bound. So if we're looking at the L infinity norm of the multiplicity function, well, there's nothing to stop all the tubes from intersecting at a single point. So the best we can do is bound the sum of the characteristic functions by the cardinality of the tube set. Now, the cardinality of the tube set T is going to be bounded above by delta to the minus n minus 1. And that's because the tubes are direction separated. So this is the maximum size of a delta separated subset of the sphere. So we have this very trivial estimate. And what we can do is, well, let's pretend we have the conjecture and we interpolate between the conjecture and this trivial estimate. So this is going to give us a whole range of inequalities with this parameter P now. And when P is equal to n over n minus 1, we have this very difficult conjecture. But at the other end of the spectrum, when P is equal to infinity, we recover this completely trivial bound, okay? So I've just carried on that expression from the previous slide. So the name of the game now is to obtain partial results on this conjecture. And the idea is that we want to prove a range of these LP estimates for P bigger than some P star. And we want to push P star down as low as we can. Okay, so if we can push P star all the way down to n over n minus 1, that's magic, we've solved the conjecture. Okay, but we're not going to be able to do that, but we're going to try and get as low as we possibly can. So a lot of people have worked on this game of pushing down this P star exponent. I'm not going to give a full survey here, but there's many works dating all the way from Cordoba's work in the 70s to the present. But previously, at least in high dimensions, the result to beat was due to Katz and Tau. So they proved this Kakeya maximal inequality holds for P bigger than some number. It's not too important what it is for the purpose of this talk. So it's 1 plus 7 over 4n plus 3. And this is some exponent that's kind of gives a highly non-trivial bound, but it doesn't go all the way down to this n over n minus 1. Now, I want to make some comments about this Katz-Tau theorem. So the proof is based on some kind of elementary arguments related to additive combinatorics, and in particular the theory of some difference bounds. And I want to mention that the arguments heavily exploit this distinct directions hypothesis. It's totally baked into all the arguments. So it's hard to say anything for more general sets of tubes. Now, of course, the whole problem relies on this distinct direction hypothesis in order for it to be non-trivial, but somehow the arguments are really kind of inflexible in this regard, and that's something I want to highlight here in order to contrast with what follows. So the theorem I want to advertise today is from a couple of years ago now, due to myself, Keith Rogers, and Rushang Zhang. And we proved that these maximal estimates hold for P bigger than some of them with Pn, which is given by this kind of horrible expression. So this, we don't have, unfortunately, a clean rational expression in terms of the parameters in the problem. We have this expression that involves a min-max. But in any case, this turns out to give the strongest known bounds for this maximal problem when n equals 5 or n is bigger or equal to 7. I don't want to give this too much weight, the fact that it improves over the Katz-Tau paper. Somehow we're approaching the problem from different directions. So, I mean, I don't have any deep philosophical reason why one approach should give better results than the other. I think this was just kind of a happy kind of outcome that it did. Now, we can also apply this theorem to get partial results on possibly the more famous Kakeya set conjecture. And this gives us the strongest known bounds to the Hausdorff dimension of Kakeya sets for an infinite sequence of dimensions. But again, I'm not sure if there's any deep, meaningful reason why this argument happens to be better than the previous arguments. It's just approaching it from a different direction. One important thing to mention is that this theorem was also independently proved by Josh Zahl at the same time, and so some aspects of our arguments are different, but at the core, as you'd imagine, since we both have this weird numerology, the ideas are essentially the same. So somehow this theorem was ripe for the picking at the time. Okay, so I want to make some further remarks. So our approach is based on this polynomial partitioning method, which has had an important, profound impact on harmonic analysis and combinatorics in recent years. And in particular, our methods are based on Guth's approach to the Fourier restriction problem and various refinements to this approach due to myself and Keith Rogers. Now, our arguments are in some sense more robust than those of Katz and Tau. So in particular, we can weaken the direction separation hypothesis and deal with more general sets of tubes. And indeed, a large portion of the argument applies to arbitrary collections of tubes. So somehow the direction separation hypothesis isn't so heavily baked into the analysis. So our work also provides a nice structural statement about extremal tube configurations. So if you imagine that we're close to, or if we have a hypothesized counterexample to the Kakeya conjecture, we can kind of read out from our argument certain structural properties this counterexample would have to satisfy. So this could give, this could provide a first step in future arguments in order to get further improvements if you wanted to argue via proof by contradiction, because then you can assume all these structural statements on your set of tubes. Okay, any questions about this before I move on? Okie dokie, so for the rest of the talk, I want to try and give a very, very high level overview of some of the ideas that go into the proof of this theorem. So the proof is fairly technical, and I'm going to sweep a lot of details under the rug, but hopefully you can get a sense of for what's going on here. To begin with, I want you to imagine you're looking at this problem and we have this collection of direction separated tubes. And when we first look at the problem, it looks like a complete mess and we don't really know what to do with ourselves. So there's no apparent structure whatsoever when you first look at this problem. But the idea in this argument is to identify some nascent structure in the problem. And this goes back to what I was mentioning earlier. So if we assume there's a counterexample to the Kakeya conjecture, then it can't be given by just a random configuration of tubes. These tubes must have some very special structural properties, okay? So the first step in the proof is going to be to isolate what these structural properties are, and that will give us a foothold in the rest of the problem. So to show this statement precisely, we're going to use this polynomial partitioning method. And this polynomial partitioning method was originally introduced by Guth and Katz in their solution to the Erdős distance problem. And Guth and Katz were in turn inspired by de Vere's solution of finite field Kakeya conjecture. So there's a nice kind of circle of ideas that have inspired one another. Finite field Kakeya conjectures inspired these developments in combinatorics, which have in turn inspired work in the continuum setting. Okay, so the idea behind polynomial partitioning is to use a divide and conquer style argument to bound the quantity under consideration. So here we want to look at this LP integral of our multiplicity function. And we're going to divide it up by breaking. Oh, sorry, maybe I'll wait a second before going. So we're going to divide it up by breaking up the domain of integration into smaller pieces. So to carry out this division, we're going to use a polynomial. This is a polynomial in the polynomial partitioning. So given a real polynomial of n variables, I'm going to let ZP denote its zero set, its vanishing set. So this divides Rn into disjoint regions, which I'll denote by OI, and we'll refer to these disjoint regions as cells. So the cells are just the connected components of the complement of the zero set. Now, of course, here we don't want to take an arbitrary polynomial. We want to take a polynomial that's adapted to our problem. And there's this nice theorem of Guth, which I've written in the particular context of these maximal bounds, but it applies in much more generality. So this theorem says that there exists a polynomial of degree at most d, where some d is some prescribed parameter, such that the following hold. So first of all, this polynomial is going to break the space up into a large number of cells. And what large means for us is d to the power of n. So breaking up into many pieces is good for us because we want to divide and conquer, and the more we divide, the stronger the position we're in. And secondly, if we look at the contribution to our LP integral over a given cell, so that's this integral on the left-hand side over OI, then this is approximately equal to the global integral divided by the number of cells. Okay? So this partition is breaking up the mass of this multiplicity function into equal portions because it's an even distribution. Okay, so I want to make a couple of remarks about this theorem. So this is based on the polynomial ham sandwich theorem of Stone and Tukey, which in turn is based on the Borsuk-Ulam theorem about continuous maps from spheres from topology. So I want to mention this here is that we see that some kind of non-trivial topology of Euclidean space is playing a role in these arguments, and this harks back to the initial discussion about Semeredi-Trotter and how Semeredi-Trotter relied on the topology of the Euclidean plane. Okay. Are there any questions about this? Okay. So what we'll actually work with, rather than the partitioning polynomial, rather than the zero set and the cells defined earlier, are these shrunken cells, which are obtained by fattening up the zero set. So here I'm going to take into account that we have this scale delta playing a role in our problem, which is the width of the tubes. So we'll replace the zero set ZP with this delta neighborhood, and we'll replace the cells with the kind of resulting cells, which are a little bit shrunken. Now, the reason for introducing this Fattened neighborhood is as follows. So we have this very elementary, but nevertheless fundamental and important observation that any tube can enter at most d+1 of these shrunken cells. And the reason for this is very simple. So if we look at the core central line of our tube, that's the dark green line in the picture, then in order for the tube to pass from one cell to another, the core line must necessarily pass through the zero set of the variety, okay? And because of the fundamental theorem of algebra, a trivial version of the Zeus theorem, we know that this core line can intersect the variety at most d points, unless it's completely contained in the variety, okay? So either it passes through the variety at most d points, which means the tube can enter at most d+1 cells, or the core line is completely contained in the variety, which means that the tube doesn't enter any cells because it just lies along this fattened, it lies inside this fattened neighborhood of the variety. Okay. So this we can interpret as some kind of orthogonality between the cells. So any given tube, if we fix a cell and we look at the tubes that intersect that cell, then they can't intersect too many other cells. Okay. So there's some kind of independence between all the different tubes. This independence is quantified in terms of this parameter D. Okie dokie. Okay, so at this stage, the argument splits up into two cases, what are referred to as the algebraic case and the cellular case. In the algebraic case, the mass of this multiplicity function concentrates inside what we refer to as the cell wall, which is this fattened up the neighborhood of the zero set of the polynomial. And there's also the cellular case, which is the complement of the algebraic case. So in this case, the multiplicity function, the mass of the multiplicity function concentrates in the cells. And then also as a byproduct of our choice of partitioning polynomial using this theorem of Guth, we know that in this case, the mass is evenly distributed amongst these shrunken cells. Okay, so we have this extra property in the cellular case. So for the purpose of this talk, I'm going to begin by focusing on the cellular case. So in this, when we're in the cellular case, we're going to home in on a given cell. So we'll home in on OJ here, and we'll look at all the tubes that intersect this cell. Now, as I mentioned before, we have this kind of orthogonality property, which is arising from Bezout's theorem. And this says, this suggests at least that we can treat each of these collections of tubes, T or J, individually. Okay. So there shouldn't be too much interaction between the tubes from these different T or J. So I want to try and give you an idea of how this orthogonality principle works in practice by a kind of thought experiment. So here I'm stating a trivial bound for this Kakeya maximal inequality. So here omega is just the union of the tubes in our collection, and we can bound any LP norm by the measure of omega, which is the supporting set of the multiplicity function raised to the power of 1 over p, times the cardinality of the tube set. Okay, so this is just pulling out the L infinity norm of the function in the LP norm, and then then we have the factor that corresponds to the support of the function. So I'm going to write this trivial bound in a way that slightly mirrors the formulation of the Kakeya maximal conjecture we saw earlier. So in particular, I introduce this factor of delta to the minus n minus 1, and by multiplying, dividing, and then I interpret one of these powers as this kind of sum of volumes of the tubes raised to the power 1 over p. Okay, so basically we can trivially go from this trivial bound to this kind of restatement in the second equation. And the point of this is that once we write the inequality in this form, we see that we're essentially off by a factor of delta to the n over p. Okay, so we have this omega to 1 over p. We can just bound this by 1 and imagine it's not there. And then we see we're missing, we fall short of the conjecture by a factor of delta to the n over p. Okay, and this is no surprise because, I mean, if we prove the conjecture using this inequality, then we wouldn't have a very deep theory at all. But we've got to make up this delta to the n over p somehow. Okay, so what I'm going to do here is I'm going to show how the cellular hypothesis can improve over this trivial bound in a small way. Okay, and this will give us some idea of how this orthogonality principle works. So the way we're going to apply this orthogonality property is through this inequality here. So what I have here is, remember, these T or J's are the collections of tubes that intersect a cell OJ. So if we sum the cardinalities of these tube sets, this is bounded by D times the cardinality of the global tube set. And why is that the case? Well, it's simply the case because any tube can enter at most, say, D plus 1 of these cells. Okay, so at most constant times D of these cells. Now, what I'm going to do is I'm going to average both. Oh, if I can get the pen to work. Aha, there we are. So what I'm going to do is I'm going to average both sides of this inequality. So I'll just quickly write it out here. So I'm going to divide by the number of cells to have an average on the left-hand side. Oh. And then I'm going to remember that the number of cells is d to the power of n. So I'll write this as d to the 1 minus n on the right-hand side, okay? So on average, we have that the cardinality of one of these tube sets is bounded by d to the 1 minus n times the cardinality of the whole tube sets, okay? Now, if this inequality holds on average, then by a kind of Markov inequality type argument, we can ensure that the same inequality holds for a majority of the cells. Okay, so this average out inequality is going to hold for 99% of the cells, provided we choose a suitably large implicit constant. Okay, so there's only going to be a small proportion that are very far away from the average. Okay. So we're going to use these two statements. So let's go back to our LP integral for the multiplicity function. Right, I would like to get rid of this stuff now, but I don't know if I can do it. Ah, there we go. So we want to go back to this LP integral for the multiplicity function. So what I'm going to do here is I'm going to first break up the domain of integration into all these cells, the OJs. And remember that each cell contributes an equal portion of the mass of the whole integral. So we can bound this by the number of cells times the integral over a single cell, okay? And now what I'm going to do is I'm going to average this inequality over all what I'll refer to as the good cells. So the good cells are the 99% of the cells which are not far from the average value, for which this TOJ has cardinality not far from the average value. So the 99% of the cells that satisfy this second red box. Okay. So at this point, we can cancel out the d to the n's. And what I'm going to do on each of these, for each of these good cells, I'm going to apply the trivial inequality to the local integral over the cell. Okay, so if we apply the trivial inequality, remember, okay, so now everything's raised to the power of p. So we pull out the volume of the cell now times the cardinality of the tube set. Okay, so we apply the trivial inequalities locally. Now I'm going to pull out the maximum measure of the cell, and then I'm left with this kind of little LP sum of the cardinalities of these tube sets. So to deal with this little LP sum, well, I'm going to relate it to a little L1 sum by pulling out the maximum of these cardinalities raised to the power of p minus 1, and then we're left with this little L1 sum, okay? Now at this point, I'm going to use those two inequalities that come from our orthogonality property of the cells. So we can get a nice L1 bound directly from the orthogonality property. And you remember from the definition of these good cells, well, we also have that the cardinality of the TOJs individually are close to the averages. So we also get a bound for this maximum term, okay? So the result is that we get all these powers of D and the cardinalities of the tube sets. So I can clean up this expression a little bit and collect all the powers together. And at this point, well, we notice we get this power of the degree D, which lo and behold, well, this is a negative power or a non-positive power if and only if P is bigger than or equal to n over n minus 1, okay? So whenever we're in the range of exponents corresponding to this Kakeya maximal conjecture, then we can control this D power. And as a consequence, well, we can bound the D power above by 1, say, and we're left with this inequality bounding the LP integral by the maximum measures of these cells times the cardinality of the tube sets. So now I want to go back and compare this inequality we've obtained from the cellular hypothesis with the trivial inequality we started with. And what we see is, well, we've got a small gain over the trivial inequality. So we've gone from the volume of the union of all the tubes, omega, to the largest volume of one of these cells. And typically these cells will be kind of smaller than the global support, because we're chopping everything up into smaller pieces. So this argument represents a small gain over the trivial estimate. Now, remember, the trivial estimate was off by a factor of delta the n over p. And this small gain is just an improvement by basically a constant factor. We can only say that these cells, they're not going to be significantly smaller than omega. So on its own, this argument doesn't tell us anything. However, the power of this argument is that we can iterate. We can apply it over and over and over again. So let's explain how this iteration process works. Well, the idea here is we've tried to do this polynomial partitioning. It hasn't really worked out for us. But what we can do is now we can home in on the cells and apply the same argument within each cell. Okay. So we apply the polynomial partitioning and we break the cell up into these children cells. Okay. And again, either the algebraic or cellular case will hold within each cell. Either the mass of the integral will be supported within these children cells, or sorry, will concentrate in these children cells, or it will concentrate along the variety, the partitioning variety. So I'm just going to assume that the cellular case continues to hold over and over and over. So if we always land in the cellular case, well, we can take the cells, we can partition them into cells of cells, we can partition them into cells of cells of cells of cells of cells, and so on. And what happens is that eventually these cells will become teeny tiny little cells. And in particular, the diameters of these cells will be less than this parameter delta appearing in our problem. Okay, and when the cells get this small, well, the analysis doesn't really make any sense anymore. Like, you've become at a scale that's smaller than the width of the tubes. Okay, so at that point we stop. Now, the inequalities that I described earlier, they're all amenable to iteration. So essentially what you end up with is a bound for this LP norm of the multiplicity function, which involves now the maximum volume of these teeny tiny cells at the terminal stage of this process. Okay. And remember, these cells have diameter at most delta, so this volume is going to be delta to the n. So in this way, we obtain this factor of delta to the n over p that we were missing when we applied the trivial estimate. Okay. And you can mess around with the resulting powers, and the upshot is if we always land in the cellular case, then we can prove this Kakeya conjecture. Okay, so the cellular case somehow represents the easy case for the problem. Okay. Any questions about this? Okay. So of course, we have nothing to, there's no guarantee that we'll always land in the cellular case, and we might hit an algebraic case. So what an algebraic case means, well, at some stage of this process, when we look at the contributions of these integrals over these cells, well, the major contribution is going to become from the partitioning variety in the next stage of this process. Okay, so somehow the mass of this multiplicity function is concentrating around a neighborhood of a variety. But we can interpret this as some kind of special structure. So we found some special polynomial structure that there's some kind of correlation between this multiplicity function and the neighborhood of some algebraic variety. There's some nascent algebraic structure in this problem. Okay. So how do we proceed with the analysis in this case? Well, okay, so maybe I'll miss this part out because it's not so important. essentially, when you land in this algebraic case, the idea is to continue the argument, but now we apply the partitioning along the partitioning variety. Okay, so what we do is we home in on the neighborhood of the variety, and now the whole analysis is going to drop a dimension. Okay, so we now form the polynomial partitioning within the cell wall, and this is like partitioning a low dimensional space. Okay, so the upshot is that we have this complicated process where we keep applying polynomial partitioning. We land in these cellular cases repeatedly until we hit an algebraic case. Once we hit an algebraic case, we know that the major contributions come from this neighborhood of the variety. So the dimension drops and we start to apply partitioning within the neighborhood of the variety. So then we go through the whole procedure again. We might go through a succession of cellular cases. Eventually, we'll hit an algebraic case. So now the contributions will be in a low dimensional subvariety. So the dimension drops again, and we start to apply partitioning within this low dimensional variety. And we continue doing this. And of course, this process is to terminate because the dimension can't drop indefinitely. Okay. So this is a full kind of partitioning algorithm. And the output of this algorithm is some very complicated, relatively complicated for me at least, decomposition of these tubes, which I'll express using this notation. So we write our tube set as a union of these tube sets TZs. So these Zs are formed by tuples of nested algebraic varieties with decreasing dimensions. Okay. And the tubes in each TZ satisfy various tangency or containment properties with respect to these varieties at various scales. Okay, so this is the full structural statement that we obtain from this polynomial partitioning algorithm. Okay, so this is the whole first step of the proof. So then we come to the second step. Thankfully, since I see that I'm very close to running out of time, this second step will be pretty brief. So this gives us, so we've managed to identify some structure in the kind of extremal configurations for these tubes. Either we hit all these cellular cases and we're in a situation where we can actually prove the Kakeya conjecture, or we at some point we hit an algebraic case, but that's giving us this structural statement. Okay, and now we want to exploit this structure in somehow. So a key new ingredient when it comes to exploiting this structure is a theorem of Katz and Rogers, which allows us to control the number of direction-separated delta tubes, which can lie in a neighborhood of an algebraic variety. Okay, so if you imagine if you have many tubes that point in different directions, it's very hard for them all to be contained inside an algebraic variety. And this gives a precise meaning to that statement. So I don't really have time to go through the numerology in this theorem in detail, but basically what you get is kind of obvious if your variety is a K-plane, but to extend it to general varieties is a highly non-trivial problem. And their proof, in fact, uses rather deep results from the theory of semi-algebraic sets. So in particular, they use Tarski's projection theorem, which is kind of a fundamental result in the theory of semi-algebraic sets, and a parametrization lemma due to Gromov. Now, this theorem allows you to control situations where your tubes are aligned near a single variety, but we saw in our structural statement that we have these kind of nested families of varieties, and this nesting is kind of gives you additional information. So we actually, in our work, obtained a strengthened version of the Katz-Rogers result. And this strengthening involves these kind of nested family varieties. And it's exactly what we need in order to squeeze like every dropout of our structural statement. So this is a more technical version of the previous result. It's a direct generalization of the previous result. But it's in some sense a non-trivial generalization. Certainly we had to develop new ideas in order to prove this theorem. But at heart, we use the same tools as in the Katz-Rogers theorem. So the Gromov parameterization and the Tarski projection theorem. But yeah, in order to make use of this nesting structure, we had to cook up some new ideas. So that's more or less everything I have to say today. I'm sorry it was a little bit rushed at the end. So if you have any questions, I'll be happy to try and answer them. But thanks for listening.